Prop 43 says, in any parallelogram, the complements of the parallelograms about the diameter are equal to one another. So it introduces this term, the complements of the parallelograms that are about the diameter, that it just kind of throws us in here. It's not really defined in like the definitions. It's sort of just like, hey, we expect that you'll be able to understand what we're talking about. So what are we talking about? Well, imagine that we have just any parallelogram, ABCD, and then we have a diameter, AC, passing through the parallelogram. Choose any point that you want on that diameter. So I chose this point right here, and then draw lines parallel to the sides of the parallelogram through that point. So let's see, there's ABCD right here. I'll say this horizontal line is EF. I'll call this vertical line GH. And then that point that I chose on the diameter, I'll call that point K. All right, so the claim here, what we mean by the complements are sort of these two full parallelograms that are sort of hinging off of the bisector, the diameter, AC. So the claim is that EBGK is equal to HKFD. That's what we want to prove. Right. And so just kind of before I jump into it, this is a place where I think this is the first proposition where Euclid starts labeling or referring to parallelograms just by opposite opposite ends. So for instance, rather than calling this parallelogram EBGK, we're just going to call it BK. And then this top one, we call it KD. So what we want to prove is that BK is equal to KD. All right, so how do we do that? Well, first of all, because AC bisects ABCD, we have that triangle ABC is equal to triangle ADC. Yep. So since AC bisects ABCD, we get that triangle ABC is equal in area, and I suppose it actually is congruent to ABC. I guess it doesn't matter. ADC, what does he say? ADC or ACD? ACD. That was Prop 34 that said that. Right. Okay, and then we kind of do this similar reasoning kind of along down the line, because we have like a handful of different parallelograms. There are 1, 2, 3, 4 parallelograms inside of ABCD. 2 of those parallelograms are being bisected by that same line AC. So I'll just say, for the same reason, or kind of, I guess, identical reasoning, we would get that triangle AEK is equal to triangle AHK, and triangle KGC is equal to triangle, and I'll keep in line with the ordering of the letters that they put in the book, triangle KFC. And again, that's just Prop 34. I said for the same reason, but just to really be precise. All of that is Prop 34. All right, and let me just make sure I'm not jumping ahead. Yeah, so I'll just read here what Euclid wrote, the way that Euclid wrote it, and then I'll kind of write it the way I would write it. So Euclid said, now, since the triangle AEK is equal to the triangle AHK and KFC to KGC, the triangle AEK together with KGC, so AEK and KGC, is equal to the triangle AHK together with KFC, and the whole triangle ABC is equal to ADC. Therefore, the complement BK, which remains, is equal to the complement KD, which remains. So what is he really saying? I might write it this way. Then triangle ABC can be written as triangle AEK plus triangle KGC plus parallelogram BK and maybe I should have said more or note or something rather than then. But then, right, triangle ADC is equal to triangle AHK plus triangle KFC plus parallelogram KD. So because of all of this chain of inequalities, ABC is equal to ADC or ACD, I guess is how I wrote it earlier. AEK is equal to AHK, KGC is equal to KFC. So like we could set these right-hand sides equal to each other and we could subtract off the first two terms of each to just leave us with BK equals KD. And this is all just common notions, kind of stringing some common notions together. But would it be common notion 1 and common notion 3 would be my guess, if I remember correctly. In any case, we get exactly what we were looking for, is that BK is equal to KD, and we're talking about these two parallelograms. They have equal area. So that's what we wanted to prove. QED, therefore, etc.